So we're going to look at titrations and pH curves based off of strong acid and base interactions. After watching this video lecture, students will be able to differentiate between the titrant and the analyte, as well as equivalence and endpoint. And additionally, students will be able to identify the pH of a solution at any point during a strong titration. So let's look at some vocabulary before we proceed. So basically the titrant is the substance of known concentration that we put into the burette. The burette is a piece of glassware that allows us to deliver precisely measured volumes of the solution. And basically what we'll do is we will add that titrant into an Erlenmeyer containing the analyte. And the analyte is the substance inside the Erlenmeyer that we do not know the concentration of. In addition to the analyte, we will also add an indicator. And an indicator is an organic compound usually that will change colors when the pH of the solution here changes. Now, the end point and the equivalence point are two things you guys need to get clarified in your heads. The end point is the point at which the color change of the indicator will occur. So basically, when the color change happens, that is the end point of the titration. So you know to stop. Now, the equivalence point is when the moles of the acid and the moles of the base that you've added are equal. Now, you typically want an indicator that is going to have an endpoint that's very close to the equivalence point. This is what allows us to know when to stop our titration and subsequently do the calculations that are necessary. So although the endpoint and the equivalence point are not exactly the same thing, they should be fairly close in value, and we can therefore use that color change indicator to tell us when we can start doing equivalence point calculations. Now, a pH or a titration curve is going to be a plot or a graph where we graph the pH on our y-axis and the volume of our titrant on the x-axis. We'll utilize these curves to differentiate between various types of titrations, but they're pretty much used pretty consistently with this corresponding organization pattern. If we're going to go ahead and look at strong acid, strong base titrations here, we want to think about or start thinking about what species are present in solution. Okay, so we know that when we mix a strong base and a strong acid that we're going to get a neutralization product. So we're going to get sodium chloride, which is a salt, and H2O. And so we're familiar with this. Now, we can think about all of the ions present, or we can just think about the ones that cause the neutralization procedure, and that is the reaction between the active species. So that's going to be H plus and hydroxide coming from each of the acids in the base. When those come together, they produce H2O. Now, when we are looking at a strong titration, we're going to, of course, need some sort of indicator. Phenolphthalein is the most commonly used indicator, and phenolphthalein is going to be colorless when it is in acidic situations, and basically a light pink or dark pink color, depending on the pH, in basic conditions. Okay, so what we're going to do here is we're just going to kind of go through a case study of the titration of 50 milliliters of nitric acid with 0.100 molar sodium hydroxide. So basically we're going to look at various points along this curve and calculate the pH at each of those individual points and look at the species present in solution. So let's go ahead and look at point A on our titration curve here. Notice point A is when we have added no, or zero volume of our sodium hydroxide. Okay, and so if we look at this initial portion of the titration, what we need to think about is what's actually physically present. Okay, so at this point inside this Erlenmeyer, all we have is HNO3, right? Okay, because our acid is what we have in that container. Now, we have not started the titration, so our pH of the solution inside the Erlenmeyer is going to be based only on what's present. So since there isn't any NaOH added, we can treat this problem very easily. Okay, so what we're going to do is we're going to look at the major species present. So since HNO3 is present, we know we're going to get H plus and NO3 minus, right? Okay, so H plus is going to be the determining factor of our pH. Okay, and because HNO3 is a strong acid, we know that the concentration of HNO3 at this point in time is equal to the concentration of H plus, which will then allow us to calculate our pH. So we've been told that we are titrating a 50 milliliter volume of 0.200 molar HNO3. with our sodium hydroxide. So our concentration of HNO3 we know is 0.200 molar. Okay, and once again, since we know the concentration of this, we know the concentration of our hydronium ion. So pH is going to be equal to the negative log of 0.200, which is going to give us a pH value of 0.699. Okay, so notice before any base has been added, we have a very, very low pH, which is what we would expect for a strong acid. And basically what we're going to do is we're going to look at how this changes as we progress through this titration process. Okay, so now that we've looked at part A with only our HNO3 present in the Erlenmeyer, we're going to go ahead and look at how the solution has been changed when we start adding some NaOH. Okay, so B is the point that we're looking at here, and at this point we've added 10 milliliters of our sodium hydroxide solution. Okay, so remember, basically the species that are going to be present are going to be coming from both our acid and our base at this point. Okay, so H plus, NO3 minus, Na plus, OH minus, and of course water. Now, we know the sources of each of these components, okay, and we need to think to ourselves, are there any reactions that will occur between the species present? Okay, and of course we know that when you put two strong components together, your hydroxide ion and your H plus ion are going to come together to form H2O. Okay, so the quantity of H plus that was in the container at point A is going to change, it's going to decrease as we add our sodium hydroxide. So we need to figure out how much of the HNO3 reacts with our hydroxide ion that we are adding. Okay, so we're going to have to do a before and after mole calculation. So in order to get our quantity of our H plus and our OH minus, we're going to need to figure out how many moles of HNO3 and how many moles of sodium hydroxide are present. Okay, so what we're going to do is just a simple multiplication of our volumes times our concentrations of each species. So as you can see, we've done that here. We've taken our volume in liters of our acid times our molarity to give us our number of moles of our acid. Okay, and because it's a strong acid, we know that H plus is directly equal to that. The same way, we've done the same process with our base, and that's given us our moles of base. Now, we know that acid and base are going to react in a one-to-one fashion to produce H2O. So in this context, basically this one-to-one relationship is going to show a decrease in our H plus and a decrease in our OH minus, and subsequently the production of additional H2O. So now if we go ahead and we look at what remains after the reaction process, we're going to go ahead and just do some simple subtraction. Now, because the hydroxide ion is present in the smaller quantity, it's going to get used up first. So we subtract our number of moles of H plus from the number of hydroxide ions that are going to interact with it. We do the same thing here, and that gives us 0.00900 moles of H plus remaining and no moles of hydroxide. So now that we know the new number of hydronium ions or H plus ions that remain in terms of moles, we can figure out the new concentration of H plus remaining in solution. So our concentration of H plus ion after the 10 milliliter addition of sodium hydroxide is going to be 0.00900 moles of H plus divided by the new total volume of the solution. So we originally started with 50 milliliters. We added an additional 10 milliliters. So 50.0 plus 10.0 mils of our sodium hydroxide. That's going to give us 60.0 milliliters as our total volume of our solution. We're going to go ahead and plug that in as our new total volume, which is going to be 0.0600 liters. If we go ahead and do this math, we're going to end up with a new concentration of H plus of 0.150 molar, okay, HNO3. So this was what remains in the Erlenmeyer after the addition of 10 milliliters of sodium hydroxide. Okay. So now we know that we have decreased the quantity of, or the concentration of our HNO3. So as you can see here on this chart, the pH level has increased slightly for station B. And we can calculate that by taking the negative log of our H plus concentration. And that will give us a new pH of 0.824, which is higher than our previously calculated concentration with only nitric acid in the Erlenmeyer. What we're going to go ahead and do is look at some of the other points along the curve. We're going to go ahead and we're going to skip the calculation for C because it'll be very similar to what we just did. And we're going to look at D because this is kind of a special point along the titration process. However, the approach to the problems are very much the same. So we have now looked at point A and B on the curve. We're going to ignore C just because, it's kind of a redundancy. And we're going to skip straight to D. So basically, at this point, we will have added a total volume of 50 milliliters of sodium hydroxide to the original 50 milliliters of the 0.200 molar nitric acid. Okay, so in the same way that we did the previous problem, we need to go ahead and look at the species present. So of course, we're still going to have H plus and nitrate ion. We're going to have H2O. We're going to have our sodium ion. We're going to have our hydroxide ion. But still, the H plus and the hydroxide ion are the important species. So again, we need to figure out what is present before the addition of the 50 mils of sodium hydroxide, and of course, what the remaining species will be in terms of their mole values. Now we're going to accomplish that through the basic multiplications that we've done before, and that's going to give us the following mole values, okay? And those will be our before values that we're going to plug into this location here. And then we're going to proceed to figure out our after value that corresponds to the interaction that occurs between our H plus and our OH minus here, okay? So we're going to go ahead and calculate those, and that's going to give us 0.00500 moles of H plus remaining and 0 moles of our OH minus remaining. Okay, so we have these values. We're going to plug them into our after value here in our table. And that gives us the information we need to calculate our H plus concentration. So we know our moles, but in order to calculate our H plus concentration after we've added 50 milliliters of the NaOH, we're going to take that mole value, okay, of 0.00500 moles and divide it by the new total volume. Now guys, remember, we started with 50 mils, we added an additional 50 mils, so that gives us 100 mils of solution, and we're going to turn that into liters. So that gives us the following liter of value. We plug those in, and that gives us 0.0500 molar HNO3. So again, guys, at this point, we have once again decreased the concentration of our HNO3. And if we go ahead and plug this into our pH calculation, that's going to give us 1.301 as our pH. So once again, our pH has increased because we have made the solution less acidic by adding a base. So let's go ahead and look at our next point, which is going to be E. Okay, so now we've looked at A, B, and D. We're going to go ahead and look at the special point E along this curve. So again, guys, the approach to this problem is exactly the same as the previous examples, and we'll talk about what's special about this particular point here in a second. Okay, so again, guys, we're going to treat this problem like any of the others. Remember, H plus and NO3 minus are present, sodium and hydroxide ion are present. Remember, we're going to focus on the ones that are most important. And look at the neutralization process that occurs between these two species. Okay, so again, we have to find our beginning moles of our H plus and our OH minus. So we've done that calculation, and we've gotten 0.0100 moles of H plus and 0.0100 moles of OH minus. Okay, so this is what makes this a special point, guys. This is the equivalence point because our moles of our H plus and our moles of our OH minus are equal. Okay, so if we go ahead and plug those into our beginning, we will quickly see that when those two quantities interact in a 1-to-1 ratio, we're going to end up with basically no H plus and no OH minus in solution. So we've done those calculations, and we get 0 and 0 respectively. So at this point in time, what is determining the pH of our solution? Okay, well, the only other species present that can affect our pH is H2O. We know that our sodium and our nitrate ion are both sourced from strong sources. So H2O is the only species present that's creating any hydronium ion. And we know that water autoionizes to give us our H3O plus and our OH minus. Okay, and we know that those are related to the Kw value. If you guys recall, we have our H3O plus times our hydroxide ion concentration equaling the following constant, right? Okay, and if we go ahead and we solve for H3O plus, we know that we end up with the following value. Okay, and if we take the negative log of that value, we get a pH that's equal to 7. Okay, so at the equivalence point for strong titration, your pH is always going to be 7. Now, this is only for strong interactions, so please put that into your thought process and make sure that you store that away. Okay, so now we've looked at these points along the curve. Now we're going to go ahead and we're going to look at point F. Okay, so we've gone past the equivalence point here. All right, so guys, if we've gone past the equivalence point here, what you guys need to understand or be able to visualize and think about is the fact that we have actually used up all of the HNO3 that's present in solution. So our pH now is going to continue to significantly increase because as I'm adding more base, I am adding more hydroxide ions, which subsequently increases our pH. This is also going to change our calculations a little bit, but hopefully this will make sense to you guys. So again, guys, we have our species in solution. Still, H plus and OH minus are the only ones that matter. Okay, so we're going to look at the process associated with these again. Okay, so guys, this is just, the same type of calculation over and over again. Now, in this case, though, our before values and our after values are going to be slightly different because of what's present in solution. Okay, so if we go ahead and calculate these. So after we've calculated these, guys, what I want you to notice that in this situation now, instead of H plus being present in higher quantities, hydroxide has now taken over. So when we go ahead and we subtract this interaction here, what's actually going to happen is we're going to use up all of our H plus and only have OH minus present. So now that we've gone ahead and done that calculation, you see that we have no H plus present and we have this many moles of hydroxide ion present. So at this point, guys, we can now calculate the concentration of our hydroxide ion after we've added 150 milliliters of it to this particular titration situation. Okay, so in this case, we have our 0.00500 moles of hydroxide. Okay, and we're going to divide by the new total volume. So remember, we have 50 mils of our acid present originally. We have 150 mils of our base that have been added, so we know that we're going to have our 200 milliliters or 0.2 liters. We divide these in, and that gives us 0.0250 molar OH minus concentration. Okay, so from this we can calculate our POH, which is going to be equal to the negative log of this value that we just calculated, which is going to be equal to 1.602. Now remember, this is POH, and we've been looking at pH. So if we subtract this value from 14, we're going to end up with a pH that is equal to 12.398, okay, which is significantly higher with respect to pH than our previous examples before the equivalence point. So notice there's a huge jump afterwards, and that's because all we're doing is adding hydroxide ions to the container. So obviously pH will continue to increase as we keep adding our hydroxide ions, and obviously we'll eventually reach a certain point. But basically, as you've seen now, as you progress through this titration, you will see an increase in the overall pH of the solution. So there's some things to consider and think about when looking at strong titration procedures. Okay, so if we're looking at a strong acid being titrated with a strong base, so basically meaning that our acid is down in the Erlenmeyer, our base is being added. Before the equivalence, we're going to be calculating H plus concentration at each phase. At the equivalence point, we're using the hydronium ion concentration from the autoionization of water to calculate our pH, and our pH at our equivalence point will always be 7 for strong interactions. And then after the equivalence point, remember that we're going to be using hydroxide ion concentration and doing calculations for it because there is no longer any acid present in the solution. Now, if we were to flip this around and have base down here and acid up here, the reverse would be true. We would be dealing with hydroxide ions first and then H plus ions after the equivalence point, but our pH at our equivalence point would still be equal to 7. The last thing I want to look at is the differences between the curves depending on what our titrant is in the strong-strong situation. So if our titrant is a strong base and the unknown in the Erlenmeyer is a strong acid, we're going to start in acidic position and move up to basic position. If the titrant is a strong acid and the unknown in the Erlenmeyer is a strong base, basically we're flipping this process. But once again, guys, the equivalence point is the same for the strong-strong interactions with a pH of 7.